All right. So here we've got in the lab, we've used those little green carts. Okay. Well, you may or may not have noticed they have magnets in one end of them. Okay. So you can actually take two of these carts, and if you bring one close to the other, it'll push it away, even though they're not touching, because the magnets are set to repel each other, which is pretty cool, because then you can like have collisions where one cart comes in and the other one bounces off and they never actually touch. Okay, so you can get really high coefficients of restitution in your collisions this way. All right, so this problem is all about taking two of these carts, and one is holding still at first, and the other one, well, this one's holding still, and this one's going to crash into it like this. And then we want to see what happens after they collide. Okay, so let's set up our before and after picture. So that helps us get everything straight. So we're going to have, I'll call it A. It's going to be moving this way, and I'll call it VA initial. And it's going to be moving in there at 2 meters per second. So I'll put 2 on there. And it's going to crash into B. And VB initial 0. Okay. So it's going to be holding still. So then what we want to know is afterwards, we've got A here. Okay. What's its speed? Okay, we'll assume it's going to go this way. And what's B's speed? Okay. And we'll assume it's going to go this way also. Okay. So we got to find both of these things. Okay, so what we do is let's just dive right into it like we have been. We've got our picture. We've got the masses. Okay, the mass of each one is 0.75 kilograms. So we come in here and we start off with our momentum. Our initial is our final. So we're going to have MA VAI. Now VB, it doesn't have any momentum, so I'm not going to write that in there. It's just 0. We would just toss it out anyway. And we're going to end up with MA VA final plus MB VB final. Okay, there we go. All right, so now, well, look at that. Look at that. Look at that. Look at that. See, I don't know this and I don't know that. The only thing we know are the masses and that velocity. So that means we got 2 unknowns and only 1 equation. So that's intractable. That's not solvable. Okay. And so what we're going to have to do is we're going to have to come up with another relationship. And this is an elastic collision. And so we do have another relationship that we can use. And that relationship is the restitution relationship. So we can say delta V final is minus epsilon delta V initial. Okay. So we can put that in there, where epsilon is our coefficient of elasticity. Now, this one, it doesn't say, hey, your coefficient of elasticity is blah, blah, blah. It doesn't say that. So what are we going to do? Well, okay, if it says perfectly elastic, that means that my coefficient is equal to 1. Okay, we got that. We know that there. Okay, so now let's keep going here. So what I'm going to have is I'm going to have VB A final minus VB final is minus 1 onto VA initial minus VB initial. Okay, just like that. Now look what we got. Now here's 2 unknowns. Whoops, not that one. Just kidding. There we go. Now I've got 2 equations. One here, and 2 unknowns. So that means algebraically I can solve this. And they're both linear, so that's pretty straightforward. Let's go ahead and put in some numbers here. So I've got in this first equation here, all my masses are going to cancel each other out, right? That's gone, that's gone, that's gone. Because they're all the same. They're all 0.75. Okay, so that means we can just write this then as VA initial, which is 2, okay, has to be equal to VAF plus VBF. Okay, so we've got that relationship there. All right, down here on the other side, if we put in our numbers, we're going to have VAF minus VBF. Okay, so that guy is a 0. There's a 2, so that's equal to minus 2. Okay. All right, now I've got two linear equations. Here and here. Okay. So I'm not going to go through this. Okay. You should be able to solve one of those. You should be able to solve that set of equations on your own by hand. Okay. And what you do is you just solve one of them for like maybe 2VAF, and then substitute that into the other one. So just a process of elimination kind of thing. There's probably 2 or 3 good ways, easy ways to do that. Now, I did it on my calculator, and you're welcome to do that too, and you're welcome to do it on a test. What I would need you to do on the test is you get to that point, and then you say, used calculator. Okay, and then you tell me what your numbers are. Okay, now when you do this, what you end up getting is you end up getting that VAF is 0 and VBF is 2. Okay, so which is pretty cool. All right, and that tells us that when this guy comes crashing in here, it's like they trade places. Comes in, goes out, just like that. Okay, and if we reverse time, we could go backwards with it, boom, boom, and it would work that way too. Okay, so as long as we have a perfectly elastic collision and the masses of the two are the same, boop, boop, that's what we're going to have there. Okay, we could have made it any speed we wanted to. It wouldn't have mattered. In the end, we would have still gotten that they sort of do this little thing like that. Okay, but now I'm interested in making this a little more general. Okay, so if we got one cart still and another cart's going to come in and hit it, okay, is there kind of another way to do that? And there is another way to think about that. And so what I'm going to do is I'm going to take this equation here at the top right, and I'm going to divide by MA. Now remember, MA is the cart that is doing the crashing. Okay, it's the one that's moving initially. So what I end up getting here is I end up getting VAI is VAF plus VBF MB over MA. Okay, so my equation on the lower left down here, it's not affected by that change at all. Okay, but the equation in the upper right is the only one where we put the mass into it. Okay, so what we've done now is we've set up a condition where we can say, well, what's the ratio of the incoming mass to the stationary mass? Okay, and we can monkey around with that ratio and we can see what that does to our final velocities. Okay, so let's do this first. Let's make A heavier than B. So let's make A the ratio of A to B a 2-to-1 thing. Okay, so we're going to say down here, we're going to say let's let MB over MA equal a half. Okay, so it's twice as heavy. All right, so what are the outcomes if we do that? So if we do that, then what happens with our outcomes is we end up getting that VAF. Okay, so that's the cart that was moving. Instead of stopping completely, it ends up going forward still, but much slower. Much slower. Okay, and VB ends up going at 2 2/3. Okay, so it ends up going faster than the cart was originally coming in. So it was originally coming in at 2, and it pops off there at 2 2/3. Okay, 2.7. Shoots out of there. All right, so that's pretty cool. So big heavy one comes in, boom, that pops off just like that. All right. Now I I actually saw that with people one time. These two little kids we had in our Taekwondo school, and one of them was this little girl, and she was a tiny thing. She's probably a 4th grader, and probably weighed about, I don't know, let's say 50 pounds. Okay. Tiny little thing. And then we had this other kid who was a 4th or a 5th grader, and he might have been a 6th grader. He was a big boy. He was probably 150 pounds. And we were doing some activities one day, and the two of them ended up kind of facing away from each other, but walking backwards, not aware of the other person. So here was the big boy and the little girl, and it was kind of like this. It went, do, 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 ping. And she went flying. Whoa! I about lost it. It was so funny. I was like, momentum. You gotta love momentum. Anyway, so let's try a different scenario. If we let MB, let's switch it around. MB over MA be 2. So now the one that's coming in is lighter than the one that's stationary, okay? And let's see what that does. So if we run the numbers on that, what we end up getting is the cart that came in, cart A, it actually bounces backwards. Okay, it actually bounces backwards, and the stationary cart B ends up going forwards, but not too fast. Okay. Just like that, not too fast. All right. And so it's kind of fun. Anyway, so you can play lots of different games with that. So if the incoming cart is a lot heavier, what does that do to us? Okay. And if it's really heavy, if it's coming in here like this and it hits a very light object, the light object's going to it's going to really take off. And the big object's going to hardly move at all. And so that's actually used, if you've ever heard of, like, with sending probes out into the solar system, or just kind of some science fiction stuff. They talk about gravitational slingshots. That's kind of what they're talking about. That's the basis for that. So you got a big heavy planet coming along. Maybe it's coming this way, and then you have your little spacecraft. And your spacecraft comes along and you sort of go woo around like that. Well, that's like a collision. And if the planet's moving this way, then this guy's going to get a real big lift out of that. So it's going to go a lot faster because of that boost there. And on the other hand, if you wanted to slow down, you just come at it from this direction. Okay, here, and then it's going to end up getting slowed down that way. So you can use those gravitational slingshots. Anyway, so if you ever see or hear anything about that in a science fiction movie, that's real. That's the real deal. And this is how it works here. Okay. Okay. So let's see here. I think that's all on this one. Yeah, I'm just going to do one more that's sort of like this. This one has gotten a little bit long, so instead of making one gigantic recording, I'll split it into 2 for you there, okay? So one more video after this.